Here we will look at variable mass systems, which will include things like rockets. Rockets. First, I want you to consider the following. What happens to the acceleration of a rocket as it burns its fuel at a constant rate? Does the acceleration remain constant? Does it increase or does it decrease? And put your answer in the Google form attached. Now, before we get into rockets, we're going to consider the general and more proper form of Newton's second law, where the net force is the rate of change of momentum. We can then take momentum as simply mass times velocity, use the product rule, and multiply that out. So we get two terms. This right here is the conventional term, mass times acceleration. Then if we allow, in general, mass to change, we do get a second term, which depends on the rate at which the mass changes. We can consider three simple cases. The first is what we've been doing so far, is we've assumed the mass is constant, so the second term is 0, and we just get F equals ma. We can also say, well, what happens if I want to keep the velocity of an object constant as its mass changes? We can then calculate what force do I need to apply to keep this changing mass moving at a constant rate. Note, if the mass is increasing and there is no force acting, the conservation of momentum says that increasing mass must move at a slower velocity to keep momentum constant. But what if I don't want the object to slow down? I do need to provide a net external force, and this form of Newton's second law tells me how hard I have to be pushing to keep the object from slowing down. The last thing we can consider is, in fact, what if I have an object that I want to be accelerating, but I'm now going to worry about the fact that its mass will also be changing. And that's what happens with a rocket. Now, technically, when you're driving your car, you are burning gasoline, exhaust gases are going out the tailpipe, and the mass is, in fact, changing. However, the mass of the gasoline versus the mass of the car is very small. So we can treat a car as essentially moving with a constant mass. For rockets, we can't do that. For rockets, the fuel will be somewhere between 2/3 and 90% of the initial mass. So the fuel is a large fraction. We cannot ignore the changing mass. Now, before we go over the math of this and applying Newton's second law and conservation of momentum to rockets, let's just consider briefly what a rocket is. Here, rockets always contain some fuel. That could be hydrogen, it could be kerosene. And because they're going to be going up high in the atmosphere and including leaving the atmosphere, it needs to bring a source of oxygen with it, so it contains an oxidizer. That could just be liquid oxygen. Those are both fed into what's called a combustion chamber. Right here is where a chemical reaction takes place. In this combustion chamber right here, temperatures get very high, and therefore there'll be very great pressures on the combustion chamber. Note we have an opening at the bottom. The opening at the bottom means the pressure at the bottom is unbalanced by the pressure at the top. That's what's going to give us an unbalanced upward thrust. Pressure up here is not balanced by pressure at the bottom. The nozzle basically just allows the escape gases to increase speed. And this is what we're going to consider. The U sub E is the speed that the gas molecules leaving the rocket engine have. That will come from the chemical reaction that takes place in the combustion chamber. For our purposes, this is just a number you look up depending upon what type of fuel you're burning. Are you burning kerosene? Are you burning hydrogen? Now let's go over some notation that we're going to use in order to apply these ideas to figure out, okay, how much faster is my rocket going to be going? Well, first we're going to consider, for simplicity, a rocket that's out in the middle of interstellar space. So we do not need to worry about gravity. The only force that's going to be acting will be the force that the rocket engine produces, both on the gases that leave the rocket as well as the rocket itself. So, some notation. The frame of reference we're going to be used will attach to a distant star. It will be an inertial frame of reference. V will be the rocket's velocity. U will be the exhaust gas's velocity. S will represent the star's frame of reference. R will represent the rocket as a frame of reference. Noting that U sub E is in fact the absolute value, because it's the speed, of the fuel with respect to the rocket. Another bit of notation. The engine's going to burn some fuel. We're going to call that delta M. Since M is the rocket's initial mass, delta M will be negative, which means delta M is the change in the mass of the rocket, that is negative, minus delta m is the amount of fuel leaving the engine going out down here. Minus delta m, therefore, will be positive. That's an important sign convention to keep in mind. Okay, now with that notation in mind, we're going to apply the conservation of momentum. We consider our system to be the rocket and the fuel. We're going to measure the momentum of our system relative to this distant star, our inertial frame of reference. Initially, the rocket has a certain amount of momentum, which is its initial mass times its initial velocity, measured relative to the distant star. Then it's going to burn some fuel. So its mass will be a little bit less, remembering delta m is negative, and presumably its velocity will have increased by a little bit. And this is what we want to find. By how much does the rocket's velocity increase? So it's its initial velocity plus this gain. This is how much momentum the rocket has. Our system, however, in order to use the conservation momentum, has to include the fuel as well. This minus delta m, remember, is a positive number, times this right here is the velocity of the fuel with respect to the star, because that's how we're conserving momentum, is by measuring momentum with respect to a distant star. However, we don't know what that is. So we need to use our relative velocity equation in order to relate that to things that we do know. So the velocity of the fuel with respect to the star equals the velocity of the fuel with respect to the rocket plus the velocity of the rocket with respect to the star. This will convert this velocity in the star's frame of reference to the velocity in the rocket's frame of reference. This right here is just minus u sub e. It's minus because u is a positive number. It's the speed. This right here is the velocity. It has to include the fact that the fuel is going out the tailpipe or going in the negative direction. And this right here is just the velocity of the rocket with respect to the star. So then we're just going to take and use the conservation momentum, that this initial momentum must equal that final momentum. So we plug all of that in. The initial momentum equals the final momentum. Now we just have some messy math to do. So here I've just reproduced the equation, plugging in right here the velocity of the fuel with respect to the star. Then we just have some algebra. Just multiply all of this out. So here I've got two expressions. I distribute everything out, and here I just distribute that out. And then we notice we get some simplification. These two terms are on opposite sides of the equal sign. They will cancel each other out. In addition, right here I have positive delta m times the velocity of the rocket with respect to the star. And here I have the same term with a minus sign. So those two terms are going to cancel out. This, therefore, is all I'm left with. However, we're going to let our changes in velocity and our changes of mass become infinitesimally small. This middle term right here is therefore the product of two extremely small numbers. That will make it vanishingly small, and we're going to ignore that. So what we're left with, therefore, is just these two terms. So this is what we have, and we're going to first consider letting these two become infinitesimally small. So this becomes a dv and this becomes a dm. Divide both sides by an infinitesimal small amount of time to get the rates at which the velocity is changing and the rate at which the mass is changing. Notice this right here is the mass of the rocket times its acceleration. Well, that would be the thrust applied by the rocket engine. And that will equal the escape velocity of the fuel times the rate at which the rocket is losing mass. So remember, this right here is a negative number. Delta m is negative, which means dm dt is negative. That makes the thrust, thankfully, positive. This is the product of two negative numbers. So here we have a formula for calculating the thrust of a rocket. Now let's return to the original equation, which is just basically m times dv equals minus u sub e times dm. That is basically a differential equation relating small changes in velocity to small changes in mass. Divide everything out so I collect my terms together. So here I have all the velocity terms together, and here I have all the mass terms together, remembering mass is changing. Then what we're going to do is integrate this differential equation from the initial state to a final state. In the initial state, the rocket will be moving some initial velocity and have some initial amount of mass. Then later it'll be moving at a higher velocity but have less mass. So when we do this integration, the integral of just dv is just delta v, and the integral of dm over m is just the logarithm evaluated at the final and the initial mass. However, the final mass is smaller than the initial mass, so this logarithm is negative, which cancels out that negative sign, To make it look so this doesn't look like a negative number, I'm going to basically just flip this ratio right here, so this is now a positive number, noting that m sub I is greater than m sub f, because this is the initial mass of the rocket, and that's the final mass of the rocket after the fuel has been burned. Here, one thing to note, which is to the dismay of rocket scientists, namely, how much velocity I gain increases only logarithmically with the amount of fuel that I burn. So it increases very slowly, which is unfortunate, but that's what the math tells us. Now, let's consider an example. And for an example, we'll take the booster rocket that's used on the space, or has been used on the space shuttle. This is its mass at launch. Of that, this much is fuel. The solid rocket fuel is burnt so that the escape speed of the gases is 2,500 meters per second. That's U sub E. This is its nominal thrust, and this rocket burns for about 120 seconds. So all this fuel is burned in 120 seconds. What I want you to do is find what is delta V, and then estimate the thrust of this rocket. Enter those two numbers onto the Google form that this video is attached to. And here's the answers. Delta V we just plug in is just U sub E, this number, times the ratio of the two masses. So that's the 5,900, which is the total mass we start out with, minus what we end up with, and we get that the change in velocity is 4,700 meters per second. Now that, of course, would be if we were to launch our rocket in outer space, not from the ground. Then we can estimate the thrust by calculating roughly what R would be. That's the amount of fuel that we're burning divided by the time that we're burning it for. R is the rate of change of the mass. That's about 4,200 kilograms per second. We plug that into the thrust equation, and we get a bit over 10,000 kilonewtons, which is a bit less than what we're seeing right here. However, this is a solid rocket booster. In solid rocket boosters, the fuel is not generally burned at a constant rate. So therefore, this thrust right here will not match this thrust. This assumes everything is constant, but they roughly agree. Now I want you to do a second example. Here we're going to have a completely different type of variable mass system. Here we've got a railroad car, and we're going to be adding mass to it in the form of this sand. And the sand's going to run out at a rate of 100 kilograms per second. And what I want to do is I want to keep this railroad car moving at a constant 5 meters per second. The railroad car is a mass of 1,000 kilograms. We'll assume that the track is level and frictionless. Find how much force I have to apply to keep this railroad car from slowing down, and enter your number to the Google form attached. And here's our answer. The force is just V times dm dt. That's what we started out with. And that's just the velocity, 5 meters per second, times the mass, which is 100 kilograms per second. That means we have to apply a force of 500 newtons. That will keep the velocity constant.